just to show that I can quote scripture with the best of them. Here's a quote from Bohr.
Ah, the Church of Satan.
Right. No. I didn't say what kind of scripture. Right.
Hello, this is Robinson Erhardt here with the introduction to Robinson's podcast number 210. And this episode is with two of my friends and recurring characters on the show, David Albert and Tim Maudlin, two of the leading philosophers of physicists out there. David is the Frederick E. Woodbridge Professor of Philosophy at Columbia University, and Tim is Professor of Philosophy at NYU and founder and director of the John Bell Institute for the Foundations of Physics, of which David is also a faculty member. They have both been on the show many times. This is David's 7th appearance, Tim's 6th, but they were last here together way back on episode 67, which consisted in an overview of the foundations of quantum mechanics. And that conversation was a lot more beginner friendly than this one, and may be a better place to start if you're not familiar with some of the basics of quantum mechanics. Because in this episode, we double down on QM and talk without much by way of introduction about the measurement problem, the role of philosophy in physics, various thought experiments like Schrodinger's cat and Wigner's friend, and we talk about Niels Bohr's effects both on quantum mechanics and the philosophy of science, and a whole lot more. You will have heard me mention the John Bell Institute many times now if you've been listening to the show for a while, but if you enjoy these conversations on the foundations of physics, then please check out the JBI, which provides a home for research and education in this area, and it is very much needed. Donations are extremely useful as the JBI is getting its footing and working on finding a permanent home, and there's a link in the description that you can follow for that. Other than that, there are two things to mention. I am in desperate need of ratings on Spotify and Apple, where I am hovering at a personally devastating 4.9 stars. So it takes approximately 1.7 seconds. That's what the latest research tells me, to leave a rating. And if you've been listening to and enjoying the podcast, I would so greatly appreciate a 5-star review / rating. Second, I have decided to try doing a monthly Ask Me Anything episode in addition to the regular weekly shows. If you follow the link in the description to the Robinson's podcast Patreon, you can currently leave a question even if you are not a member, and I will record and release the episode at the beginning of July. So if you're interested in joining the Patreon, you can also do that there, where you will get a link to an ad-free RSS feed and show notes for all new episodes. Now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with David and Tim. So, Tim, you said that you wanted to get us started with these 3 quotes you've picked out to lay the groundwork for discussing the measurement problem.
Yeah, so let me just get this out of the way because I think it should come up. And it's just because you said that the topic was going to be the measurement problem. And there have been many comments, some I think right on target, which illustrate that maybe the term the measurement problem is not the best term to be using here. And so I just kind of wanted to run through those 3 comments very quickly. So one is a comment that apparently Einstein made directly to Heisenberg. This isn't written down, but just in conversation. at a time when Heisenberg was trying to develop, I guess, matrix mechanics and so on. And my guess is that what Heisenberg was saying was, well, I really want my theory to be framed just in terms of observable quantities or measurable quantities, right? This kind of logical empiricist notion that you want to stay away from theoretical entities and stick with what's observable. And apparently Einstein made a comment that impressed Heisenberg so much that he reported it in his autobiography. And what Heisenberg reports is that Einstein said, it may be heuristically useful to remind oneself what one is really observing. But from a fundamental standpoint, it is entirely wrong to want to build a theory only on observable quantities. For in reality, it's exactly the other way around. It is only the theory that decides what one can observe. So Einstein's saying, look, you have to specify the theory, and you do that without mentioning what is or is not observable. And then it's by analyzing the theory that you've specified that you figure out what's observable or what's measurable, right? So that's the first quote. Now, that quote is actually referenced in the second quote, which is from John Bell's wonderful paper against, quote, measurement, where he's laying out what he thinks are mistakes when you're trying to understand quantum theory. And he says what you want is a precise fundamental physical theory. And he thinks that if that's your target, there are certain words you just must avoid. So I'll just read a little bit of this paper. So he says, here are some words, this is Bell, here are some words which, however legitimate and necessary in application, have no place in a formulation with any pretension to physical precision. And here are the words: system, apparatus, environment, microscopic, macroscopic, reversible, irreversible, observable, information, measurement. The concepts system and apparatus, environment, immediately imply an artificial division of the world and an intention to neglect or take only schematic account of the interaction across the split. So you shouldn't, a fundamental theory should not mention a division into system or apparatus, right, or system and environment. The notions of microscopic and macroscopic defy precise definition, obviously. So also do the notions reversible and irreversible. Einstein said that it is theory which decides what is observable, and I think he was right. So that's Bell's reference to this very quote, right? It's theory that decides what is observable. I think he was right. Observation is a complicated and theory-laden business. Then that notion should not appear in the formulation of a fundamental theory. Information? Whose information? Information about what? On this list of bad words from good books, the worst of all is measurement. It must have a section to itself. So now you have the section entitled Against, quote, Measurement. When I say the word measurement is even worse than the others, I do not have in mind the use of the word in phrases like measure the math and width of the Z boson. I do have in mind its use in the fundamental interpretive rules of quantum mechanics. For example, here they are as given by Dirac. Any result of a measurement of a real dynamical variable is one of its eigenvalues. That's a quote from Dirac. Here's another quote. If the measurement of the observable is made a large number of times, the average of all the results obtained will be. And here's another quote. A measurement always causes the system to jump into an eigenstate of the dynamical variable that's being measured. Now we're back to Bell. It would seem that the theory is exclusively concerned about, quote, results of measurement and has nothing to say about anything else. What exactly qualifies some physical system to play the role of measurer? Was the wave function of the world waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer for some better qualified system with a PhD? If the theory is to apply to anything but highly idealized laboratory operations, are we not obliged to admit that more or less measurement-like processes are going on more or less all the time, more or less everywhere? Do we not then have jumping all the time? The first charge against, quote, measurement in the fundamental axioms of quantum mechanics is that it anchors there the shifty split of the world into system and apparatus. A second charge is that the word comes loaded with meaning from everyday life, meaning which is entirely inappropriate in the quantum context. When it is said that something is, quote, measured, it's difficult not to think of the result as referring to some pre-existing property of the object in question. This is to disregard Bohr's insistence that in quantum phenomena, the apparatus as well as the system is essentially involved. If it were not so, how could we understand, for example, that, quote, measurement of a component of, quote, angular momentum in an arbitrarily chosen direction yields one of a discrete set of values? When one forgets the role of the apparatus, as the word measurement makes all too likely, one despairs of ordinary logic, hence quantum logic. When one remembers the role of the apparatus, ordinary logic is just fine. In other contexts, physicists have been able to take words from everyday language and use them as technical terms with no great harm done. Take, for example, the strangeness, charm, and beauty of elementary particle physics. No one is taken in by this baby talk, as Bruno Tucek called it. Would that it were so with measurement. But in fact, the word has had such a damaging effect on the discussion that I think it should now be banned altogether in quantum mechanics. So that's why if you talk about the measurement problem, you're likely to think that the notion of measurement must be involved, and this is a bad idea. And the last quote is just something that the physicist Philip Pearl said, which I think sums up the situation. He said, quantum mechanics doesn't have a measurement problem. It has a reality problem. That is, it's not at all clear what the theory postulates as actually existing. And you can say that without mentioning measurement, without mentioning observation, or any of these other terms. And if you don't solve that problem, then you just have literally no idea what you're talking about. So all of that was, I hope, a useful prelude that will avoid some pitfalls if we're going to talk about something we're going to call the measurement problem, but we should be aware that it's not really a problem about measurement. It's a much deeper problem. End of sermon.
David, did you have any comments?
I mean, this will also emerge. It goes without saying that Tim and I are in complete agreement about substance here, about what kind of theory physics should be aiming for, and about what kinds of words don't belong in the fundamental formulation of such a theory, and so on and so forth. As to whether, I don't know how to put this, and I guess this will emerge in the details we discuss later on. This phrase, the measurement problem, refers to an episode, a very prolonged episode, in thinking about the foundations of physics, that I think is really important, and in which a lot was at stake. Okay, so there's a distinction between figuring out what words you want to use in a proper formulation, in a proper, mature formulation of a fundamental physical theory. And on that, Tim and I have been, as long as either of us can remember, in complete agreement, I think. And I endorse everything that Tim says. But if you say, I'd rather not discuss anything called the measurement problem, you're going to be leaving out an episode in which something quite enormous was at stake. And there being as much at stake as there was is one of the things that attracted me to thinking about foundations of physics in the first place. if you just call it the reality problem, if you just say, look, what we should be thinking about is what's really there, of course that's right. What's really interesting, and this emerges a little bit in the way Heisenberg was representing himself in the conversation with Einstein, what it obscures is that there was a long period in the history of physics, very much under the influence of Bohr, notwithstanding Bell's complimentary remarks about Bohr in the passage that Tim read. There was a long period when something more was at stake than just, okay, what's the proper description of the world going to end up being? Okay, something was at stake of the form, what can we hope to get from science in the first place? Does the scientific project as traditionally conceived survive our encounter with subatomic particles and so on and so forth? So using a term like the measurement problem alludes to this period when something gigantic was at stake, not just about the output of the project, but about the nature of the project itself, about what we could hope for from the project, about what the project was entitled to aspire to, so on and so forth. That is captured by a phrase, I think, like the measurement problem. So once again, Tim's the views that Tim has just endorsed in these quotes about the appropriate place for a mature fundamental formulation of a physical theory to end up, I agree with 100%. But that agreement is, but talking about something called the measurement problem evokes a debate about precisely that question. What should a physical theory look like? What can we hope for from physical theories in terms of their relationship to reality? Okay, blah blah blah, and that's and for my money, the bigger issue about the foundations of quantum mechanics was not how's it going to end up? Are there waves? Are there particles? Are there waves and particles? Blah blah blah. That's all, of course, profoundly interesting, and something that both Tim and I have spent a long time working on. But there was an even bigger question looming in the background. Is this the right way to formulate physical theories? Can we hope for physical theories which are formulable in that way? And I'm sure we'll have the opportunity to talk a lot about that over the next hour or two. But for that reason, I would very much use a phrase like the measurement problem to refer to what was at stake in a debate that I was very deeply interested in.
I mean, there's a rhetorical point, and then another point I can make very quickly. The rhetorical point is, I thought calling it the reality problem made it a much bigger problem than calling it the measurement problem, right? So
yeah, I guess I disagree with that.
I know you disagree with that, but that's not the way I hear it. And the way to illustrate that is actually sitting on Robinson's T-shirt. Okay.
What does it say?
Well, I think I have to speak to get the camera on me, but
right.
Tell Schrodinger I am live.
Right. So there was a problem illustrated famously by Schrodinger in his paper in response to the EPR paper, where he brings up this cat example. And in a formal way, he talks about an experiment which involves a piece of radioactive material and a Geiger counter and a diabolical device. We all know that. Formally, that experiment is not in quantum mechanics a measurement. It's not a measurement of anything. Okay, that is, you can do experiments that are not measurements. I mean, I can give you an experimental protocol. Here's one. Take a coin, put it on your thumb, flip it so it turns at least 5 times in the air, let it land on a flat, hard floor, and record whether it comes heads or tails. That's an experimental protocol. It'll have an outcome. You can record the outcome as data. It isn't a measurement of anything. It just doesn't measure anything. If I flip the coin 1,000,000 times, maybe it'll measure a bias in the coin, but one flip is not a measure of anything. And so the problem of the cat had nothing to do with measurement because the cat wasn't being measured. The problem with the cat was that the damn cat should end up either alive or dead, period, end of story. That's I call that in one of my papers, the problem of outcomes. You think that experiment should have an outcome, which is either a live cat or a dead cat. And if your physics doesn't give you that, then Schrodinger's view was your physics is obviously, radically, terribly inadequate, right, to describe the physical world. That's not a problem about measurements because that experiment just isn't a measure. And so I think one needs to keep a focus on that part of it. And the term measurement brings with it other considerations that are actually kind of irrelevant if you're worried about, I want my cats to end up alive or dead. Because why? Because cats end up alive or dead. That's why.
I'm not sure this is going to be a productive road to go down, but I'm a little puzzled by what you just said, Tim. If somebody were to construe the cat experiment as concluding with a measurement of the aliveness of the cat, or if somebody were to construe the coin flip experiment as concluding with the measurement of the orientation of the coin, would they be severely distorting the situation somehow?
It would be severely misrepresenting the experiment.
What? So I guess yes, but
normal experiments, it's a setup situation and then a result situation, and the experiment is the entire process from beginning to end. Now, you may want to say that, the end of it is yet another measurement of something, although, try and write down a Hermitian operator for the aliveness or deadness of a cat. Good luck with that.
But we don't have good reason for doubting that such an operator exists.
Sure we do. I think we have every...
What do you have in mind?
Now we're going to get into technical stuff about what there's good reason to believe they're Hermitian operators for, what there's good reason to believe they're positive operator valued measures for. We could, arrival time experiments that...
Okay, let's keep away from that. Right.
A whole technical thing we could devolve into, which is actually extremely important, but not, I think, at the level we want this podcast to be. I just think if you think the problem is illustrated by Schrodinger's cat, there's just not any reasonable sense in which that setup measures that whole setup from beginning to end, right? You put the cat in the box. It's alive at the beginning. The point of that setup is not to measure anything about the cat. Right? The point is to kill the cat or it doesn't kill the cat, right? That was Schrodinger's point.
Like I say, this is going to carry us too far afield. Maybe you and I should chat about this sometime, but I'm not sure in either of those cases why it would be a crazy distortion of the situation to describe those procedures as a preparation and a measurement, as a preparation followed by a measurement in the usual laboratory way. But look, let's maybe it's not going to be productive for us to go there.
One final point. Let's at least acknowledge that some ways of understanding quantum mechanics just have it that you start with one cat, you end with one cat, and that single cat is either alive or dead, and that's just a physical fact. And that's sort of the way we think the world is. And of course, there are the many worldsy kind of approaches which deny that and say something like you start with one cat and you end up with infinitely many cats, one of which is alive and many of which are dead in different ways. Mm-hmm. And that is certainly not the way we think the world is. And you're going to have to do some pretty severe mental gymnastics to turn such a theory into a theory we can connect up with the world as we think it is. And I think you can say all that without talking about measurement. You're just talking about cats. That's all.
Yeah, I think you could say it without talking about measurement. Yes.
Well, especially the early portions of the quote by Bell point out a lot of the culprits for what seemed to confuse discussions of the, and I'll use air quotes here, the quote unquote measurement problem. And I hope we'll come to rehash the issues with terms like system and observable and measurement and so on. But for now, just to get everyone on the same page as us, especially our listeners without a background in quantum mechanics, I think it would be really good to begin by situating the measurement problem historically. So just what was the state of physics leading up to the realization that there was this problem to be answered? And as David, you already described it as a very long and pivotal period in the development of the physics.
Well, I think, and Tim may well know more about the history, the details of the history than me, but the way it's usually presented is something like this. There's a Stanford textbook presentation of quantum mechanics, like you get in treatments like Dirac, that Tim was just quoting, or something like that, where you can break it down into roughly 5 principles. There's a principle for how you're supposed to mathematically represent possible states of physical systems. You represent them either by wave functions or by vectors in a certain kind of vector space called a Hilbert space, and so on. There's a way that you're supposed to represent observable properties of physical systems, and as Tim said, this is a way of formulating a theory, a way that both Tim and I would profoundly object to, okay? But a way of formulating a physical theory that one would adopt if one were in the grip of some kind of logical empiricism or some kind of idea that the questions that physics is supposed to answer for us are questions about how measurements come out, or something like that. Good. So there's a principle about how you're supposed to mathematically represent states of physical systems. There's a principle about how you're supposed to represent observable properties of physical systems. You're supposed to represent them by means of mathematical objects called Hermitian operators that operate on these wave functions or operate on these vectors in a Hilbert space, on these mathematical objects that you use to represent physical states. There's a certain principle called the eigenstate-eigenvalue link, which tells you under what circumstances a certain vector in this state space can be associated with determinate values of the observable property of that system that's represented by this particular operator. So there's a whole mathematical machinery there. Then there's a dynamics, okay, which is represented in the non-relativistic case by, say, the Schrodinger equation, or more generally by some differential equation, which says how the wave function evolves with time, or how the state vector, in that way of representing it, pivots as time evolves, points in different directions. All the physical information is supposed to be encoded in the direction in which the state vector is pointing. So there's a dynamics, and that dynamics has 2 very vivid and important properties. One is that it's completely deterministic, and the other is that it's linear. Okay, good. Then there's another prescription about what happens to the state of the system when you do a measurement of a certain operator. Okay. And the prescription stipulates that when you do a measurement of a certain, you approach a system which is in one of these physical states, represented by one of these vectors or one of these wave functions. You perform a measurement on this system, okay? And there is a prescription which tells you the probability given the state of the system, the state that the system was in just before you did the measurement, and which one of these Hermitian operators the measurement was a measurement of. There's a prescription which depends on those two things, which tells you the probability that the measurement will have one or another of its physically possible outcomes. Okay. And this principle, called the collapse of the wave function, also stipulates that when you do one of these measurements and you get an outcome, the system discontinuously and stochastically jumps from whatever state it was previously in to the state in which it has the measured property, the property that you just found it to have, or that you just recorded it as having as a result of the measurement you did. Okay. Then the system evolves between that measurement and the next one in accord with the linear deterministic equations of motion expressed by these differential equations, and so on. Okay. Those, in a nutshell, are the sort of basic principles of the standard textbook formulation, a formulation we've had since sometime in the 30s, in standard textbooks since sometime in the 30s, with books like Dirac's book or von Neumann's book, so on and so forth. And the problem that was referred to as the measurement problem is that one doesn't know, is that there appear to be two claims in this standard textbook formulation about how quantum states or quantum wave functions evolve in time, okay? There's one claim, which at least when you first hear it, seems to be presented as fully general, which is that it evolves in accord with these linear deterministic equations of motion, the Schrodinger equation in particular. The second one is this claim about how the wave function evolves when a measurement is done, okay? Whatever the hell that word might mean, okay? And that claim is neither deterministic nor is it linear, okay? That claim is explicitly stochastic, discontinuous in a way that evolution, according to the Schrodinger equation, never is, nonlinear, so on and so forth. So there is, on the face of it, some kind of a problem about how you're supposed to put these two things together, okay? That is, there is, on the face of it, some kind of a flat-out contradiction among these various principles that I just listed. And it's that situation, or the question of how to respond to that situation, or what to say about that situation, or what to do about that situation, which, insofar as I understand it, which is what was traditionally referred to as the measurement problem.
I think that to further supplement this picture of the historical and theoretical development of what came to be called the quote-unquote measurement problem, and I'll drop the air quotes now going forward, it would be good for our listeners to hear a more concrete description of what this might look like in practice, either with a description of a real experiment or an idealized experiment or a thought experiment or something like that.
Yeah, well, maybe it would be, in a way, the point that David just made is the point that Bell made in the one part of what I read. So maybe we can, but his point is very concrete, right? So maybe this will help, and if it doesn't, then we'll try some other way into it. So yeah, if you open up von Neumann's book, Mathematical Principles of Quantum Mechanics, and you just look at what he has to say about theory, it's kind of this remarkable thing that he says there are two different kinds of time evolutions in this theory, process 1 and process 2. And he calls them that. And process 2, I think, I might get them, mixed up. Anyway, one of the processes is what David said. It's evolution that's specified by the Schrodinger equation. That's a nice linear differential equation. It'll make this wave function evolve in a nice, smooth, deterministic, predictable, linear way. And then there's this second kind of evolution, the collapsy evolution, which is not deterministic, it's stochastic, it's not linear, it's essentially in every possible way, completely different from the first kind of evolution. So you've got this kind of Frankenstein monster of a dynamics that has two different dynamics that have been sewed together, and you wonder, well, when does what happen, right? And the official answer is it's all the one way until you make a measurement, and then it's the other way. And then Bell's and he says, well, if I think of measurements or observations as having to do with, say, what someone observes or someone is conscious of, that means for billions and billions and billions of years since the Big Bang, it was all this smooth evolution, and there's no fact about whether any stars formed or how many or where there were planets or anything, right? There are no facts about that, given David's principle, the eigenstate eigenvalue link. None of those descriptions could possibly have been true. The whole physical universe was this kind of amorphous something. And then you say, until what? Well, one question is, as Bell says, well, until the first amoeba, evolves, until the first human evolves, or what? But then you can say, well, how can amoebas even evolve? Because there aren't any, well-distributed pre-amoeba pieces that can join together. I mean, there's just nothing going on. Right? No chemistry in the normal sense. No stars, no nothing is going on until there's a measurement. But then how can you ever get to the point where a measurement occurs? Now, there's one obvious way out of this, and it solves part of it, but not the other part. And this is something that David worked on a lot. One way out of this is to keep this dual dynamics of smooth jump, but decouple the jump from anything to do with measurement or observation or anything else, right? Just decouple it entirely. And you say something like, yeah, these jumps happen, and they just happen randomly with fixed probability per unit time. That's the GRW approach. So the word measurement and observation is completely gone. These jumps would be happening in the early universe all the time. You wouldn't have problems with stars forming and things like that. So you kind of can solve a bunch of things by that particular route, which is why Bell was so impressed by the GRW theory, as you'll read in his paper, Are There Quantum Jumps? But there's yet another problem if we try to keep the rest of the principles, because as David mentioned, there was this so-called eigenvalue, eigenstate link, which says the only time a system even has, say, a position is when its wave function is in an eigenstate of the position operator. And if you ask, when does that happen? The answer is, on this GRW kind of picture, never. Things will never have positions. You'll never get into that state. In fact, you kind of better not ever get into that state. When will things ever have momenta? Answer, never, right? They may have some kind of weird properties that we don't even know how to describe. And there may be some sense you can articulate in which those properties are sort of close to position or close to momentum, although all of that becomes rather difficult. So even if you solve the when does it happen problem in this very blunt, it happens at random fixed probability per unit time way, you're still left with a bunch of problems if you try to stick with all the other basic axioms that David mentioned, right? There's still work to be done. David did a paper with Hilary Putnam called The Tales of Schrodinger's Cat, which was all about this problem back in, the 80s. So this was part of, where he cut his teeth, was trying to get, find a way through that particular thicket.
Sorry.
No. So anyway, I just want to say that statement of the problem, again, measurement is gone out of even the statement of the problem. I would say a reality problem is much closer to what it is, right? Okay, now you have a dynamics, but what the hell is really going on, right? How do we connect that dynamics to the world as we are familiar with it?
I think it might be worth backing this up a little bit. First of all, let me try to address what you were asking for, Robinson, just a minute ago, a more concrete example. Here's a concrete example of the way this was usually applied. I have I don't know what. I have a particle which is emitted from some point, and its wave function spreads out in space, and that in a certain moment I do a measurement which confirms that it's located within some small subset of the space to which its wave function has spread out. The spreading out is the evolution in accord with the Schrodinger equation. The Schrodinger equation always makes highly confined wave functions spread out in space. You might at some point do a measurement, find that the result of the measurement indicates that the particle is actually located in some small subregion of the larger region over which the wave function has now spread out in accord with the Schrodinger equation. And what the collapse postulate tells you is on learning the outcome of that measurement, or on performing that measurement, or I don't know what, the wave function, in violation of Schrodinger's equation, discontinuously contracts to a function which is non-zero only in the region where you found it to be. And where you did find it to be was going to be a matter of chance. You might have found it here, you might have found it there, you might have found it there. So the wave function abruptly and non-deterministically contracts again to a small ball as a result of the collapse postulate, and then starts spreading out again, okay? And if you're going to do another measurement of its position later on, you will have from the collapse postulate and something called the Born rule, a set of probabilistic, stochastic, chancy evolutions, discontinuous and nonlinear evolutions that it might go through on the occasion of that second measurement, and so on and so forth. So that's a sort of concrete example of the way these two things are put together in the lab. But I also want to back up a little on the description Tim gave. There's Tim, I think, characterizes exactly correctly the way this is laid out in the context of, say, von Neumann's book on mathematical foundations of quantum mechanics. What you have there is a situation where von Neumann says, well, look, there's this Frankenstein monster, as Tim very nicely put it, of a theory, okay? There's a certain way that the quantum state behaves when it's not being measured, and there's another way that it behaves when it is being measured. And von Neumann, just as Tim says, calls one of them process one and one of them process two. And when you put it that way, it sounds like the problem that you're trying to solve is a problem of trying to precisely delineate the location of this boundary between those circumstances in which the Schrodinger equation holds sway and those circumstances in which the collapse postulate holds sway, those circumstances in which process one holds sway, and those circumstances in which process two holds sway. And to the extent that you're treating the situation that way, as von Neumann does, you're in some sense trying to solve what Tim calls the reality problem, okay? Trying to answer questions however unwieldy they are, about what's actually going on. Okay. And you might conclude after a little worrying about this, that this is the wrong way to approach it. And you ought to take a different approach, like Tim says, characteristic of something like the GRW theory, where you don't tie this second process to the occurrence of a measurement because you realize you just don't know how to set in a reasonable way the location of this boundary between those circumstances in which the collapse postulate applies and those circumstances in which the Schrodinger equation applies. And you might be on the road to the development of all kinds of theories. But look, the sense in which I just said I wanted to back up a little bit is that I think there was an enormously influential point of view, which I associate with Bohr, okay, which is not on board with this von Neumann view, which is not on board with any sort of realistic attitude towards what's going on of the kind which would result in your feeling pressure to answer questions like, I wonder exactly where this boundary is, okay? I wonder exactly where to draw the line between those circumstances in which the Schrodinger equation applies and those circumstances in which something like the collapse postulate applies. Von Neumann is already somebody who feels the weight of that question, okay? But I think Bohr, who I see as way, way more influential throughout most of the 20th century than von Neumann was in this respect, is thinking that even formulating the question that way betrays a kind of naivete about what the aspirations of the scientific project can possibly be, okay? I don't think Bohr saw it the way von Neumann saw it at all. I mean, let me, just to show that I can quote scripture with the best of them, here's a quote from Bohr.
Ah, the Church of Satan.
Right. No. I didn't say what kind of scripture. Right. Here is the next to last paragraph. And I always took it the most important one in Bohr's response in 1935 to the famous EPR paper challenging the completeness of quantum mechanics. I think the next to last paragraph, the one I'm going to read, is much more important than the last one. The last one wanders off into issues about general relativity, which aren't really relevant here. Here's what I take to be the climactic paragraph in Bohr's paper. Bohr says, this necessity of discriminating in each experimental arrangement, that is, this is one of the things that Bell cautioned us never to do. This necessity of discriminating in each experimental arrangement between those parts of the physical system considered which are to be treated as measuring instruments and those which constitute the objects under investigation may indeed be said to form a principal distinction between classical and quantum mechanical description of physical phenomena. It's true that the place within each measuring procedure where this discrimination is made is in both cases largely a matter of convenience, while, however, in classical physics, the distinction between object and measuring agencies does not entail any difference in the character of the description of the phenomena concerned. Its fundamental importance in quantum theory, as we've seen, has its root in this is a big phrase with Bohr, the indispensable use of classical concepts in the interpretation of all proper measurements, even though the classical theories do not suffice in accounting for the new types of regularities with which we're concerned in atomic physics. And here's the money quote. In accordance with this situation, there can be no question of any unambiguous interpretation of the symbols of quantum mechanics other than that embodied in the well-known rules which allow to predict the results to be obtained by a given experimental arrangement described in a totally classical way. This is a very explicit and very dramatic disavowal of the whole realist scientific project, it seems to me. This was Bohr's reaction to the measurement problem. And this is something that I think gets at what was at stake in discussions of the measurement problem. Somebody like von Neumann, as monstrous as his theory is, as Tim rightly says, is already in the realist camp, okay? He's trying to say, he's not trying to confine himself to claims about how measurements come out. He's trying to say something about what's actually going on in the world. Well, sometimes the wave function changes this way, and sometimes the wave function changes that way. Bohr thinks that even going remotely that far is a huge mistake, okay? Bohr thinks that even the monstrous Frankensteinish kind of realism that von Neumann is presenting us with already represents a failure to learn the real lesson of the so-called measurement problem, which is that you ought not to be trying to solve what Tim called the reality problem at all. Okay, that's the wrong place to start. The right place to start is the place where Heisenberg seemed to be starting in his discussion with Einstein. Okay, and that's what I think is at stake. Okay, that's why I think, as it were, if you construe the reality problem as the problem of saying clearly what is the reality, that's ignoring the even bigger debate which is occurring in the background of this, which I associate with the phrase the measurement problem, which is whether that's a problem that physics, can or should aspire to solve in the first place.
Okay, so
that's my sermon.
Let me just make a couple comments here, which will also take us back maybe where Robinson wanted to begin, back in history a bit. Well, first of all, I think Bohr says a bunch of different things in a bunch of different places that can't be put together into a single coherent story, right? So you can, the devil quotes scripture, or you can quote the devil's scripture for whatever you want. Probably find him saying it somewhere. There's a curious thing about the particular paper you mentioned, which was Bohr's response to the EPR paper, because the title of the EPR paper is Quantum Mechanical Description of Reality Complete. And on the attitude you're suggesting, the answer should have been just like one sentence. No, of course not. We were never looking for such a thing, right? Who would think it was complete, right? Who would think that you could read off all the physical facts about a system from this, because that wasn't but that's not Bohr's response. I mean, he's going to a great deal of effort to give a different response. Let me now go back even a little more in time. There was a big deal about this collapse of the wave function from the beginning. It was the very thing that bugged Einstein from the beginning.
Right.
And this, again, is not to do with what we would normally call a measurement. So Einstein said, all right, this is, like the beginning of the Schrodinger cat setup. Take a single radioactive atom of uranium, stick it in the middle of a big spherical detector, and wait. Now, that turns out not to be representable quantum mechanically, really, as a measurement of anything. But you know what will happen if you wait long enough? A spot will appear somewhere on that sphere. If you do it many times, the spots will be evenly distributed over the sphere. They'll arrive at different times and so on. And what the Schrodinger evolution is doing, all before the spot forms, is, as it were, the wave function, which begins very concentrated at the center of the sphere, is, as it were, slowly leaking out in a spherically symmetric manner, just constantly at a certain rate, right? And that, notice, that doesn't break the spherical symmetry at all. And from that wave function, you then can calculate a probability at any given time that a spot will appear here or here or here at that time. Now, Einstein then said, but wait, that can't be a complete description of what's going on. I mean, it's not that something's slowly leaking out of this thing. I mean, Einstein's thought was, look, it's a radioactive atom. At some point, an alpha particle or whatever just breaks free. It's bouncing around inside somehow, and it jiggles its way free, and it shoots off in some direction, and then it hits the sphere. But a moment before it hit the sphere, it was right near the sphere, right there, heading out in that direction, right? It was going to, Einstein, has this picture. Obviously, that's what's going on. His objection to the collapse of the wave function involves the two things he always complained about quantum theory. One was that, first of all, where that spot occurs is, as it were, fundamentally probabilistic. It's not predetermined by anything, right? It's a violation of Leibniz's principle of sufficient reason. That is, that quantum theory was a fundamentally probabilistic theory about nature, right? God plays dice with the universe. And Bohr never responded, no, of course God doesn't play dice with the universe. That's just our ignorance about what's going to happen. Bohr's response was, who's Einstein to tell God what to do, right? So, certainly the orthodox theory embraced the chanciness as a fundamental feature of nature itself. And the second thing about the collapse of the wave function was that when the spot appears here, the part on the sphere way on the other side, which just a moment ago there was a chance the spot would occur over there because this thing is leaking out in all directions, that chance immediately and globally disappears instantaneously. Gone. Right? That the collapse of the wave function is not merely probabilistic, but instantaneous and global. That's spooky action at a distance. Right? Einstein thought that just obviously violates relativity. You can't make sense of that. Really, what this wave function is just an epistemic description of what we know. It's not a description of what there is. And that's what he wanted them all to agree to. And then say, yeah, let's try and come up with theories that tell us what there is and not just what we know. And of course, we know Bohr and Heisenberg and so on push back against Einstein. I mean, if they were on the same page, they should have agreed and said, yes, of course, that's fine. Maybe they could have said, why do we care for a more complete theory? Or I just don't think physics can achieve a more complete theory. Or Einstein would have come back and said, well, why not? I mean, give it a shot, guys,
No, I agree with that.
Had a discussion.
The second response is closer to the way I see Bohr here. Certainly closer to the quote that I just read, okay? Bohr seems to think, I don't know how to reconstruct this in a rational way, but Bohr seems to think that there's a tension between, on the one hand, this sort of, I don't know if it's a priori or analytic, some kind of very deep necessity of describing experimental procedures in thoroughly classical terms, on the one hand, that if you don't do this, you just can't imagine how to do science, okay? Why that should be true, I have no idea. Clearly, by the time we get to von Neumann, he's not thinking in those terms. He's trying to describe everything in terms of quantum mechanical wave functions. It's just that he has this Frankensteinish theory about how they change with time, okay? But Bohr thinks there's this really deep tension between, on the one hand, the necessity of describing and reasoning about and communicating about experimental setups and outcomes in purely classical terms, and on the other, the inadequacy of classical physics to treat the sort of phenomena that we are confronted with in atomic physics, as he says, okay? And he thinks that this is a tension that anybody who reads this as a tension that we got to figure out how to resolve is already making a mistake, okay? That anybody who sees this rightly, don't ask me to defend this claim, but this is how I'm reading what Bohr writes. Any attempt at reconciliation, any attempt at sewing these things together a la Frankenstein or something like that is already a radical mistake, okay? That we should have learned that any such attempt will, for reasons that only Bohr can see, inevitably collapse into hopeless paradox, okay? Or something like that, okay? And that once you see this, you're going to move from an idea of the aspirations of physics as doing what Tim calls solving the reality problem, okay, telling us what the world is like, to a much more modest, much more instrumentalist in philosophical terms conception of the aspirations of physics as telling us how certain measurements are going to come out, and with a strong caution not to speculate any further than that, because that way lies madness. That way lies collapse into hopeless paradox that you're never going to find your way out of. You're absolutely right that what Einstein would say to that, and rightly so, especially given the way subsequent history has gone, what Einstein's going to say is, gee, are you sure about that? I mean, are you sure this is going to inevitably collapse into hopeless paradox? Because it turns out nowadays, we know by explicit construction that that's not true, okay? We have a bunch of solutions to the measurement problem that work at least for the sort of non-relativistic quantum mechanical phenomena that Bohr and Einstein were discussing at the time, a la the GRW theory, which you mentioned, or Bohm's theory, which we haven't mentioned yet. So sure, I agree with that. But I think Bohr's view was anyone who saw this rightly saw that this was not a problem to be solved, okay? This was a confrontation with the limits of the depth to which the scientific imagination could even in principle penetrate.
Okay, so let me, and again, I hadn't anticipated this devolving into Bohr exegesis, but which is, I think, kind of a hopeless task. But let me at least put a couple data points or possible observations here. So one thing you said was that you were very puzzled about why Bohr would insist that the experiment be described in classical terms, right? And there are two ways of hearing that demand. And in one way, I don't think makes any sense at all. And the other way, I think, does make sense. The way that doesn't make sense at all is if you think by in classical terms, I mean using classical dynamics like Newtonian mechanics. That is using classical dynamical principles, F equals ma. But it seems to me that's not what he needs to mean. I'm not sure if he was clear about this. But suppose I do an experiment and you just ask me, okay, what did you just do, right? Describe the experiment to me. And I say, well, I took a little piece of uranium and I stuck it here and I put a big spherical shell around it. And I waited to see when a spot formed and where it formed. Now, that description doesn't involve any dynamics. I mean, I haven't postulated Newton or anything else. It is, in a certain sense, in classical terms, that is, in the positions and behaviors of macroscopic objects, right? And I mean, this is the sort of thing that Bell talks about. When I describe the experiment, I have to say, these switches were switched this way and this much current was running through these wires.
But I don't know.
And I can see, let me just finish it. Yeah. I can see all that without specifying the dynamics. But if I can't even use that language in describing the experiment, then I don't know how to get across what I even did. And you can sort of see how physics would devolve into a Tower of Babel if I'm not allowed to say that kind of stuff.
Yeah, but I think somebody like von Neumann would already have said, what's the impediment to understanding everything you just said as approximate descriptions of quantum states of various macroscopic systems, as opposed to approximate descriptions of locations in classical phase space.
I-
This has nothing to do with dynamics.
I'm not sure how that conversation would go, but let me just give one other data point, which is that the Bohr you imagine is a very modest guy, right? He says, look, we've reached the limits of what the human mind can accomplish. We shouldn't try to go beyond those limits.
Right.
The ship will sail over the edge of the world or something.
Right.
But there's this other part of Bohr which I don't see how to reconcile with that. And that's, he thought that this principle of complementarity that he had discovered was the fundamental mystical key to all of reality, that it applied not just in quantum mechanics, but everywhere, that the concepts of life itself was complementary, right, of being alive was complementary to having a precise description of the cellular workings, right? The idea was something, if you set up a situation where you can figure out what the cell is doing, you of necessity have to kill it. Now that, of course, just turns out to be completely ridiculous and absolutely wrong. And we know by electron scanning microscopes and what we can do nowadays, that's just completely idiotic.
Right.
But Bohr said it, right? And Bohr not only, he thought it was profound, right?
First of all, I agree that
family seal that he did. So that's not a modest, like, I'm not going to make deep claims about the world guy. That's a,
no, I mean, look,
about the world you can imagine.
I agree with you that it's probably not the most productive direction for this conversation to go to devolve into Bohr exegesis. But I'll just say quickly and then drop it. I don't see any tension between what you've just pointed to about complementarity being an extremely broad business and the way I was reading Bohr here. But forget about that. The way Bohr came up here is by way of my explaining that what the term the measurement problem evokes for me, okay, is a very deep debate about what one could hope for from the scientific project, okay? Even deeper than a debate of the form, what are the deliverances of a properly conducted scientific project about whether the world is made of waves or particles and waves, or, what the fundamental ontology is. That's the answer to the reality problem. I saw what was at stake in the measurement problem as a question about whether science could even aspire to answer what you're calling the reality, to Tom, what you're calling the reality.
Maybe this can be the last comment on this topic and we can go somewhere else. On your reading of this, I take it, you then think the measurement problem is over and done with. It's set.
Yeah, in a certain sense.
There's nothing left of it, right? These actual constructive theories,
right,
that what Bohr said couldn't be done, right, are object lessons that show he was just wrong. And we really don't
I'm this construal of the
just wrong, right?
Exactly right. I agree. Yeah.
Okay, good. I think we can leave Bohr aside at this point then. I mean, if you think his conclusion was wrong, it doesn't really matter how he got there.
Good.
David, when you were reading a few minutes ago the quote from the Church of Satan, you said afterward that Bohr's remark marked a disavowal of realism. And what this made me wonder more generally is what the attitude among physicists, if there was one, going into this debate over the collapse of the wave function, what it was. Like, did physicists have a belief about what they were doing in the scientific endeavor writ broadly that Bohr was repudiating, or was this question of realism new for physics and they were just confronted with it by the phenomena to be explained?
I think there was at least an implicit, I mean, once again, this is a detailed historical question, but I guess my thought has always been that there was at least an implicit idea that people were operating with. That, yeah, what are we trying to do with fundamental physics? Trying to say how the world is, okay? We're trying to say in a fairly literal, straightforward, flat-footed way how the world is, okay? And yes, I think what made there be so much at stake, at least for somebody like me, in the reaction of people like Bohr and the huge majority of the physics community that Bohr carried with him for so much of the 20th century. Bohr was, needless to say, there's a long history of philosophical conversations about realism going back as far as one likes. And there are all kinds of philosophical critiques of realism and so on and so forth. What seemed to be astonishing about the way Bohr and Heisenberg and so on were talking was that, yes, there had been this happy, maybe not so deeply philosophically reflective, although in many cases it was deeply philosophically reflected. But anyway, yes, there was a working assumption in physics that what we're trying to do with fundamental physics is find out what the world is like, okay? And of course, there was this long history of philosophical critiques of realism. What was shocking about the way quantum mechanics was described was that it was the first occasion where, like they, to continue this horror movie theme, the call is coming from inside the house, okay? That certain empirical discoveries had somehow made it clear to people like Bohr, who had thought it through, that this realistic project had collapsed, okay, could no longer be pursued, okay, represented a deep fundamental mistake or hubris or I don't know what, okay? And maybe Tim can comment on this. And of course, there's a lot of more detailed stuff to say about the history of physics before the advent of quantum mechanics. But if somebody wakes up in the middle of the night and wants one sentence, we're scientists, we're physicists who were interested in the most fundamental aspect of physics, pursuing what they would have explained to themselves as a pretty straightforwardly realistic project where what they were trying to do was tell you what the world was really like. Sure, okay. And that's what seemed like it was at stake and at risk and in play in the way people like Bohr and with him much of the physics community for much of the 20th century reacted to quantum mechanics, to the development of quantum mechanics.
So can I just make, I'm not sure, I mean, this is just to try and delineate some problems one might have. If one's worried about this funny question, what are physicists trying to do, or what is physics trying to do? And you're using categories like realism as opposed to, say, instrumentalism. That discussion has been going on forever. It's nothing new about it. Right. So, we go back to Copernicus, and you say, well, Copernicus presents this model, this heliocentric model, and the Earth is spinning on its axis and orbiting and blah, blah, blah. And one way to take that is instrumentally. And that was what, when Osiander writes the preface to De Revolutionibus to try and keep Copernicus out of trouble with the church, says, I'm not suggesting this is literally what's going on. I'm just saying, if, as it were, fictionally you pretend that this is what's going on. You can then calculate where you'll see Mars and this and that and eclipses in a really efficient way. So you can always take that instrumental attitude, and you can also say, look, right now I'm just interested. This seems to be a good calculational tool. Let me calculate some stuff, and I'm happy doing that. Now, in the case of Copernicus, it's a little bit illustrative. That, well, first of all, of course, Copernicus didn't actually take that attitude at all. He thought, no, I'm actually postulating the Earth is spinning on its axis and so on. And of course, once you do that, as Galileo understood, a whole bunch of other questions come in train, like, how do the birds keep up and why do things fall the way they do? And, if the Earth is literally spinning, all right, now here are a bunch of questions you've got to answer about how the physics of a bunch of other stuff works, given that hypothesis. If you're an instrumentalist, you could just shrug your shoulders and say, I never really thought it was, I was never claiming it was literally spinning anyway. So who cares what the birds do, right? That kind of discussion has been going on. I mean, you could say the same kind of discussion with electromagnetism. Someone might say, well, I've got Maxwell's equations. I can calculate what, a bunch of electromagnetic stuff. And somebody says, yeah, but are there literally electric fields? Are these stresses or strains in a medium? Blah, 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 blah. And you could take two attitudes, right? You could say, well, I don't care. I just think this is good enough instrumentally. Or you could say, I do care, and I'm going to kind of construct a model. So these kinds of, it was not unique to quantum theory that there would be different attitudes. It may have been, Bohr's kind of approach to it might have been a little unique, but it's so obscure, it's a little hard to say. If he was just a committed instrumentalist and said, in general, I'm just an instrumentalist about everything, then you just shrug your shoulders and say, okay. But no, it seemed to be something different, right? He thought it was...
I agree. This is what I mean by the call coming from inside the house, okay? It was always clearly the case that one could take either attitude, okay? And one could have philosophical sorts of debates about what the more correct attitude to take was. Okay. It seems to me clear, that Bohr thought something different and unprecedented was going on. Okay, that the option of the realistic attitude had somehow evaporated, and paradoxically evaporated under the pressure of empirical discoveries, not of philosophical reflection.
Just to get us off Bohr for 1 minute, you say when you were doing this is what really interested in you. Yeah. To me, it was actually, I wasn't very interested in Bohr. I was more interested in Wigner. So Wigner's a guy who says, I take these collapses really seriously.
Right.
And furthermore, if you ask me when they occur, I'm going to say when you make an observation. And when you ask me when do you make an observation, I'm going to mention consciousness.
Right.
You need a conscious agent to become aware of something. And now you say, oh my God, it's the mind-body problem. Somehow the mind-body problem itself is appearing at the center of physics. That excited me, right? That I thought very interesting.
What both of our imaginations was this impression of some bigger philosophical issue than you thought you were going to run into in physics being at stake.
Yeah. Right.
I agree. We're not so different. We're not so different.
And the same kind of constructive counterexamples,
right,
that Bohr wasn't right, also show Wigner wasn't right.
Exactly right.
So if this realism-instrumentalism dichotomy was not new, is what was new a realism-anti-realism dichotomy where the anti-realism consists in something like a repudiation of the existence of underlying determinate physical facts? Is that seeming more...
I agree with Tim here. We're putting too much, Bohr... Bohr is not remotely internally coherent enough to sustain an inquiry like this. You got a guy who famously taught his students that a superficial truth is a proposition whose negation is false, and a deep truth is a proposition whose negation is also true. What are you going to do with this guy? Okay. I don't, or that clarity crowds out profundity, or some, I don't know what there's only so much that the writings of such a person, there's only so much interrogation that the writings of such a person are going to sustain before they completely fall apart.
Right.
But as foggy and confused as all this was, it's what was cited. I mean, not von Neumann, okay? It's Bohr that was cited, okay? And maybe Heisenberg, who thought he was agreeing with Bohr. It's what was cited by most physicists throughout most of the 20th century as what we've learned about the world from quantum mechanics.
Right. And there's yet another quote, which I don't have to hand, I wish I did, to this point, which was a quote from De Broglie. I saw it recently. I don't know if it was in a letter or something. I think it was in a letter. And De Broglie is saying about the historical situation. He says, some people are leaders, right? Some scientists are not just scientists, but they're organizers, right? They're leaders of movements. And Bohr was like that.
Right.
And Bohr organized with Heisenberg, even though they had internal disagreements, and created a common front and so on. And De Broglie says, I was kind of a loner. Schrodinger was kind of a loner. Einstein was kind of a loner. None of us liked what Bohr was doing, but none of us was a leader. None of us was trying to create a school.
Right.
So we were just off on our own, kind of, scattered stochastic terrorists, if you will. I mean, this, resistance was all scattered and disorganized.
Right.
The reason the Copenhagen people had such a profound influence just had to do with organization.
Right.
And I think historically that's correct. I think that's actually historically accurate because, you think of the names against it. Einstein, Schrodinger, De Broglie. These are not like fringe characters,
right?
Sniping from the outside, but they were pushed aside. And there's not really an intellectual account of that. There's a kind of political account of that.
Yeah, sociological. Yeah, I agree.
Well, maybe we can put Bohr aside for the rest of the conversation. And Tim, you mentioned that you're not interested in him. You are, however, quite interested in Wigner. We already discussed quite briefly my T-shirt and Schrodinger's cat, but Wigner's friend is another important thought experiment in the foundations of quantum mechanics that hasn't come up on the show really at all. So that might be something worth discussing, or just other things about Wigner.
Well, let me say a word about the Wigner thing. The reason I was drawn to Wigner was, I was a young guy, right? These are your youthful enthusiasms. I've always thought that the mind-body problem was pretty much insoluble. You can't even, speculatively produce a theory that you'd say, at least that would solve it. And so if you have this kind of black hole, there's a temptation to take all your other problems and throw it into the black hole and say somehow, the mind-body problem is sitting behind our problems with quantum mechanics and everything else, right? That turns out just to be nonsense, but it was very appealing to me as a young... I literally thought, oh, maybe I can figure a way to do an experiment to figure out whether monkeys are conscious, because if I can tell whether they can collapse wave functions... seriously, I thought I discussed that with somebody. I can't remember when I was young.
Well, Avner Shimoni did experiments like this in the 60s.
Yeah.
So, Avner Shimoni worked closely with Wigner. Right.
Yeah.
Right.
You can go off in that direction. Now, the Wigner friend particular example, I always find puzzling because whatever else one would think, you would think everyone would agree that what Wigner's friend does in that situation counts as a measurement and an observation. And so if measurements and observations cause collapses, then everybody should agree there will be a collapse. And if Wigner doesn't put the collapse into his calculations will just be wrong. It'll give him the wrong result. Somehow people, it's this double thinking of, well, I really need these collapses, but I don't really believe in them because I think ultimately, I can just have Schrodinger evolution all the time and it's okay. I think, what's clear is that von Neumann didn't think that. He saw the conflict.
Right.
The fun part is that in the Wigner-Friend case, it's just bringing out the psychological fact that people were double thinking, right?
We might just set up for listeners who don't know what the Wigner's Friend story is. Here's the idea. I forget who is Wigner and who's the friend, but there are two people. There are two observers.
Wigner's the guy on the outside, I think, and the friend is the lab rat.
Okay, good. So Wigner's Friend, imagine that there is some electron which is in a superposition initially of being located at point A and being located at point B. Wigner imagines that a friend of his carries out a measurement of the location of that electron. And suppose that we treat that entire measurement interaction, including the brain of the observer, as something that as a circumstance in which the quantum state of the world evolves strictly in accord with the linear deterministic equations of motion. Then the deterministic prediction of those equations will be that once the measurement of the location of the electron has been carried out and has been registered in the position of the pointer on the measuring apparatus, and once that the position of that pointer has in turn been registered in the memory cells of the brain of the conscious observer, what the deterministic equations of motion would say is that the observer and the measuring device and the measured electron are in a complicated, entangled superposition, a superposition of one state in which the electron is at point A and the measuring device registers that the electron is at point A, and the observer is aware of the measuring device registering that the electron is at point A, superposed with another state in which the electron is at point B and the measuring device registers that the electron is at point B, and the brain of the observer registers that the measuring device registers that the electron is at point B. And if Wigner were to look on the evolution of his friend and his friend's measuring device and the electron from the outside, that is, if Wigner were to place the boundary that Bohr was talking about in his quote between that system and himself, to count only himself as the real measuring device here, and to treat the whole system consisting of the electron and his friend's measuring device and his friend's brain as the system that's supposed to be treated quantum mechanically, the system that lies on the far side of the boundary between observer and observed, or between subject and object, or whatever the hell you're supposed to be talking about. If that's how Wigner treated it, Wigner would see his friend evolving in accord with the Schrodinger equation into this complicated superposition. On the other hand, like Tim said, I take it the point is supposed to be that the friend is a conscious agent, okay, must have recorded a determinate outcome to this measurement of the location of the electron, and consequently could not be part of a system which in its entirety is evolving in accord with the linear deterministic equations of motion. So the story sets up a tension, okay? The story sets up a particularly acute kind of tension between what things will look like if you're observing all this from the outside and treating it all as a single quantum mechanical system, and what it's going to look like from the inside. That is, I suppose this could be construed in Wigner's mind as presenting a particularly urgent sort of demand that, as we were talking about with von Neumann, we locate the boundary between those physical circumstances where the linear deterministic equations of motion apply and those where the collapse postulate applies. And this is supposed to set up a tension around that.
I want to. I'm not. It's been a long time since I've read Wigner's paper, so don't take this at all as something to rely on about what Wigner had in mind. But there are a couple of things I think should be said about the situation. One is that David described it in a way that's not technically quite right. That is, he says, well, if Wigner's the guy on the outside, what will he see this big wave function of the particle plus the detector plus his friend? What will he see that do? And the answer to that, you won't see that do anything. I mean, if you talk about what's observable and measurable, these kinds of quantum states are not observable and measurable. He can't do anything to determine what that quantum state is, not experimentally. It's very important in quantum mechanics that actually you can't do that.
Well, let's see, Tim. I mean, do you mean as a matter of fundamental principle, or
yes,
do you
mean as a matter
of
of
practical intents and purposes?
No, I mean as a matter of fundamental principle.
So then I'm puzzled.
There is no Hermitian operator whose eigenvalues are all the possible quantum states.
Let's see. I'm not sure I understand. There is
no operator. There is no Hermitian operator whose eigenvalues are all the possible quantum states.
I don't know how all the possible quantum states got into this. The question is
talking about what Wigner will see as the evolution of that wave function.
Oh, no. Okay, good. But let me ask a different question.
Yeah.
Is there a Hermitian operator, okay, of which the state of the particle and the measuring device and the friend at the end of this story is an eigenstate?
Yes, I mean, of course, there should be if there's no.
And so, by measuring that operator, Wigner,
because even if there is a collapse, there'll be some chance that he'll get a positive outcome for that measurement.
Yeah, you have to do it a lot of times.
You have to do it. And this is the point I'm getting to. This is just a little technical point, right?
Good.
So because it also makes the conflict here an empirical one and not just a philosophical or conceptual.
Right.
That's what I'm trying to get at. Right?
Absolutely right.
So for people who know this, and I hope everybody does, or I don't know why you're listening this long, in the standard two-slit kind of experiment, we, as it were, send an electron at this barrier with two slits in it. The quantum state under the Schrodinger evolution evolves so that there's a piece of it that goes through this slit and a piece of it that goes through that slit. And then those evolve together and they come to overlap, and then you get interference bands, right? You get this characteristic bands of very high and then very low wave function. And then if we square that for probabilities, you get these bands, right? You literally see them on the screen. If you do this over and over again, you accumulate these interference effects. If there were a collapse of the wave function right after the slits, so that what survived that was only either this piece or this piece, maybe half the time this piece, half the time that piece, not both, then you would not see those bands. The bands would never form because you would not have the the two pieces wouldn't both be there to interfere, right? So if you ask the question, I wonder if there are these collapses right after the screen, you can do an experiment and check. And that experiment will come out one way or another. If there are collapses, it'll come out one way. And if there aren't, it'll come out another. This is not something you just jawbone about, right? Or speculate about. This you can check. And the same thing would be true in the Wigner-Friend case. That is, in principle, although not in practice.
Right.
There would be a very complicated kind of experiment, and maybe you'd have to do it many, many times on the friend over and over again.
Right.
But if the friend were causing collapses, it would come out this way. And if the friend were not causing collapses, it would come out that way. And so in principle, if you talk about what's in principle observable, or in principle what you can get just kind of concrete data that'll settle, the Wigner-Friend thing should be settleable that way.
Yeah, and I agree with that. And presumably
that really tells you that it's not just kind of optional whether you put the collapses in, or it's just a matter of taste or something like that. No, this has real concrete observable consequences of putting it in.
Yeah, I agree with that, and presumably Wigner would have agreed with that. I'm also not sure exactly where this story comes up in his reasoning through to his final conclusion. But yes, yes, I agree, and Wigner would have agreed. Sure.
I'd like to return to some things that came up just a little bit earlier before we talked about the Wigner's room thought experiment, where Tim, you mentioned the mind-body problem and experiments with monkeys, and David, you mentioned von Neumann and Abner-Shimoni. And just to put a name to what I think the subtext was going on here, that's the von Neumann-Wigner interpretation.
No, those are different. I mean, at least insofar as I know, those are different. These are von Neumann and Wigner represent two different, in both cases, it seems to me, very clumsy attempts to delineate the location of this boundary that we were talking about before between those physically possible circumstances where the linear, dynamical, deterministic equations of motion hold sway, and those circumstances where the collapse postulate holds sway. Von Neumann is famous for identifying that boundary with measurements, okay? Wigner is famous for identifying the location of that boundary with conscious experience, okay? Or something like that. So both of them are in some sense moves within the same larger program, okay? That is, we've got this Frankenstein monster that we've got to sew together in one way or another, and these are two different speculations about where to put the seams. The trouble is that both speculations, forget about whether they're crazy or anything like that, they're just hopelessly vague, okay? They're not, and this goes back to the remark of Bell's that Tim read at the beginning. They don't involve the kind of language that we have the right to expect in a formulation of a fundamental physical theory.
If you read around in the literature, this difference between tying collapses to measurements and tying them to observations and then tying observations to consciousness, that comes up in the literature. So somebody like Everett or some of these people who appeal to measurement then go on and insist, look, you don't have to be conscious to be a measuring device. I mean, there's no problem with making a robot, right? A mechanical robot measuring device. So don't saddle me with this Wignerian invocation of, the mind-body problem. Whereas, as far as I know, what Wigner wanted to do was invoke the mind-body problem, in sort of the way that, I don't know, Penrose wanted to invoke Gödel's theorem as the key to something or other. And these are just very different attitudes about what people think they're doing. Even if they're all doing things that have kind of no hope of being really principled, They have no hope in different directions.
So they're quite different approaches. They share in a very similar kind of futility and hopelessness. Right.
Well, the elucidation is helpful, but where I was going is, I mean, we've already seen how things like, or terms like the Copenhagen interpretation or measurement can be obscuring rather than helpful. And for better or for worse, the von Neumann-Wigner interpretation as a term is used interchangeably with something like consciousness causes collapse interpretation.
I've never actually heard.
I just wasn't aware of that.
Yeah, I've never. Who uses the phrase the von Neumann-Wigner interpretation?
Right.
I will Google it right now, and because I know that I've seen it.
Not widely used, I can guarantee that.
Von Neumann. Yeah, there's a Wikipedia page on the von Neumann-Wigner interpretation. It's quite extensive.
Go figure.
Yeah,
David
Chalmers. About Wikipedia at this point.
Well, David Chalmers is cited as a big part in this, apparently. But anyway, my question was going to be, though, is what your motivation earlier in your career, Tim, was to pursue this, and also to ask David what the sorts of experiments that Abner Shimony was doing.
Well, I mean, look, when I was growing up, people were reading the Tao of Physics and God knows what. I mean, there was just this zeitgeist that there was something ineluctably weird and spooky and profound or whatever about quantum theory in all kinds of strange directions. And I was a young kid, right? I was some naive little guy who thought, gee, that sounds cool. Once you get into it, and then especially once you read somebody like Bell, it kind of blows all of these clouds away. And you say, look, there is a definite technical problem here. We don't have a clearly defined physical theory. And interestingly enough, it's to the opposite of Bohr, and this is what we've been saying all along, to the opposite of Bohr's idea that there just can't be one. When you start looking into it, you say not only can there be one, there can be several that are all quite different, but are clearly articulated, mathematically formulated, and empirically adequate as far as we know. So, and none of them involve consciousness, and none of them involve, some of this really weird stuff. Now, you might end up being disappointed by that. I wasn't disappointed by it. I just found it, the more I got into it, the more interesting it was. And you're puzzled that there's all of this obscurantism around the subject matter when there shouldn't be. That's how I got to where I am. But Bell's result does tell you something quite astonishing. I mean, on the other side, when I read Bell's theorem, I understood, man, this I really was not expecting. I didn't see this coming at all. And this really looks like something you can take to the bank. And that's what I've been kind of hammering on for 40 years.
David, did you have anything to say regarding what you mentioned about Shimony?
I mean, Shimony, I remember experiments of Shimony's, and these would involve departures from Wigner's point of view. But I remember experiments in which Shimony, if I'm remembering them correctly, asked some graduate students to try mentally, whatever that means exactly, to delay or to speed up the decay of a radioactive nucleus. Okay, and what I remember being astonishing about the outcome of this experiment is that they had a lot of runs. Okay, and it wasn't just that they didn't discover an effect of trying to speed it up or slow it down, but the actual measured frequency was exactly the predicted highest probability value. And I remember being in an audience where Yakira Haronov was listening to this result. And Aronoff stood up and said, "That's astounding. There's something really mysterious here, because the probability that the frequency would exactly match the probability was incredibly low. So you must have made some astounding discovery." But anyway, yeah, people ran experiments like this in the 60s, especially people like Abner, who were working closely with Wigner.
That just shows that the universe is so designed that it will maximally not do what you want it to do, but be able to do that.
Right. Something funny is going on, right? That's what Yakir said. Yakir said, "My God, this is astounding." Okay, it matches it exactly. Something really funny is going on. But this, of course, was a joke. The result was there was no measured effect.
For the last bit of time we have, I'd like to shift back to the bigger picture. And particularly, I'd like to start with something that you said earlier, David, when you said that as far as you're concerned, the measurement problem is settled. It's all been set and done, assuming I did not misquote you. But I wanted to...
Well, Tim, that was a quote that was offered to me by Tim. But I'm glad to, given the way that I set up the measurement problem, that sounds like a fair thing to say. Yes, that is, there's a question. If you're construing, as I was claiming Bohr did, the measurement problem as some kind of first encounter inside of empirical science with the limits beyond which the scientific imagination cannot penetrate, okay? Yeah, that's been settled. He's wrong, okay? The problem is not an encounter with the ineffable. It's an ordinary scientific problem like other ordinary scientific problems. Moreover, we already have a bunch of pretty good-looking, candidates for a solution on the table, okay? So you might say, there was this discussion which I was interested in. Is the measurement problem a straightforwardly scientific problem, okay? Or is it or is it something foggier and weirder, or is it merely verbal, or something like that? Yeah, that to my satisfaction, and I think to the satisfaction of everyone who studies the developments over the past 50 years in this subject, has been definitively settled. It's a scientific problem. Okay, it's not a verbal problem. It's not a philosophical problem. It's not a question of interpretation. Okay, it's a scientific problem that's going to be solved by what turns out to be the appropriate sort of modification of the existing scientific theory, a mathematical modification which hopefully, and in most cases so far does, have empirical consequences that we can in principle go out and measure. Yes, that problem has been settled. The question of which one of these modifications to the traditional form of the theory is going to turn out to be the right one, or whether any of the ones proposed so far is going to turn out to be the right one, is still up in the air, as it is with many scientific problems. And we don't know how long that'll last, and we don't know how long it'll take for the dust to settle and for this to be resolved. But a sort of ironic, poignant twist to this story is that the main contributions of philosophers or people who were working from philosophy departments, or primarily from philosophy departments, over the past 50 years or so to this discussion was precisely to insist, you know what, this is not a philosophical problem. It's a scientific problem, okay? And the contribution of philosophers was precisely to identify it clearly and unmistakably as a scientific problem.
Yeah, I agree with everything David said, except as usual, one phrase, which is David said at some point, Well, we don't know how long it will take for the dust to settle. Where, as I understand, the dust settling is actually getting empirical data that tells you, as it were, what the right solution is.
Mm-hmm.
But it's certainly possible that the dust will never settle.
Right.
Right. That's, we can't rule that out. There's no reason why we should. You could have two clearly different theories that are both perfectly adequate in themselves, but provably make exactly the same observable predictions.
Right.
So at least you can't, bluntly settle them by doing an experiment.
Right.
But that's not a surprise at all. I mean, the theory
No,
that
as you've pointed out, that happens all the time.
It happens all the time. The universe, the theory that the universe began 10 seconds ago in exactly the state that it obtained 10 seconds ago, no further experiment will settle that.
Right.
You happen to think that that's a kind of dumb theory and that you'd be kind of an idiot to believe it, but not because the experiments are against it. So we have experimental things. We have some rational principles. It may be that all of those taken together don't settle it and the dust never settles.
Right.
We should be prepared for that. Okay. We should, the world might not be kind to us.
But like you say, that's always been the case in science. That's merely to reinforce the observation that what we've got here is a scientific problem, like other scientific problems. Yes.
Is it fair to say, though, that and it usually isn't fair to say this, and I get corrected. Is it fair to say that the upshot of where we are now is the measurement problem, as you laid it out, has been sort of solved? There is now a scientific problem, but is the role of philosophers now to clarify, just what this scientific problem is, just what a solution would be like, and still to adjudicate between the different contending theories? Because this is what it seems like. For instance, David, when you and I spoke with Sean Carroll, it seems like you are disputing something about the philosophical plausibility of something like the many worlds theory.
I think, and my bet is that Tim is going to agree with this or is going to take objection to one sentence, as he often does. But I take it. My bet is that Tim is going to mostly agree with this. It contributes negatively to the advance of our understanding of these matters. To start out by trying to distinguish between the proper role of philosophers in this discussion and the proper role of physicists in this discussion. It has been of the very essence of the productivity of this field over the past 50 years that those kinds of disciplinary boundaries have largely been ignored or evaporated, okay? And you find plenty of cases of people employed in philosophy departments saying, hey, look at the empirical consequences that this proposal would have. Maybe somebody ought to go out and do an experiment like this, and so on and so forth. This is so yeah. No, I don't think I think the role of philosophers and physicists who are interested in these questions is to talk about them and try to get to the answers. And I don't see. It strikes me as unhelpful to start out by asking what's the proper role of philosophers in these conversations.
I think that maybe the problem was with my phrasing it, and maybe I shouldn't have distinguished between philosophers and physicists, but what I should have focused my question on was whether there are new philosophical problems. There's a philosophical problem of clarifying what the scientific problem is, and there are philosophical problems in figuring out which of the competing physical theories is the right one. And I shouldn't have been framing the question about the role of philosophers and physicists.
Yeah, I agree with everything David said, and I want to object a little more to what to the thrust of what you're asking. So let me try it this way. the one question is, do you want the philosopher versus physicist contrast in this thing at all? I think the answer is no. Here's a contrast which is relevant. It's one we already talked about. Are you an instrumentalist? That is your attitude, I just want to make good predictions. I just want some gadget that will allow me to make good predictions. I don't know, build bridges and, make computer chips that work. And that's all I care about. I just am not interested in how the world really is. That's one group of people. People can have that attitude. I don't understand it. It's not my attitude. It's not why I went into this. I don't care about computer chips. I don't particularly care about making predictions, except insofar as I think they're evidence for or against theories, right? Then you have the people who their attitude is, I want to kind of figure out how the world is. I want to see how far I can get in that enterprise. Probably we'll never be sure. Certainly there'll be different options, but for each option, you want to evaluate what would its empirical consequences be, what other virtues or defects of a more abstract type might it have that make it plausible or implausible. I don't think any of that is the province of philosophers as opposed to physicists, right? If you're not thinking about that as a physicist, you're not doing good physics. And if you're not thinking about that as a philosopher, you're not doing good philosophy. I mean, I just don't see that disciplinary boundary is playing any role here. I think as a practical matter, philosophers are a bit more trained to hear when words are being used ambiguously, when there's a little slip in an argument because of, equivocation or a logical slip. We're trained to do that, and sometimes we can point that out more directly than someone with a physics training can. Whereas if someone with a physics training can point out a mathematical slip more easily, there are different strengths and weaknesses that the disciplinary training give you. But I don't see any other way to divide this between physics and philosophy at all.
I still want to push back against you in the sense that I don't know if you have said this in writing or if this is just something you've said to me, but I think you have said, physicists don't understand physics. And do you think that you have not said this, Tim?
Oh, that's a sociological claim about the actual content of a standard physics training today. Physics itself as a discipline shouldn't be involved in it. It should be. It's just physics has gotten sick, right? The discipline of physics in its own terms has become ill because of quantum. We all hope, and David hopes, and I hope, to a little bit, point this out and maybe lead it in a more healthy direction. But that's just a sociological claim. It's not a claim about the disciplines per se, right? The aim of the disciplines.
Mm-hmm. I mean, there are physicists who do good physics and physicists who do bad physics, and there are philosophers who do good philosophy and philosophers who do bad philosophy. That's the distinction here, not the distinction between the proper object of study of one or the other of these disciplines. So yeah, when Tim says physicists don't understand physics, he's pointing to the fact that there are a lot of physicists who do physics badly.
Yeah. And in the other direction, what I've certainly said many times publicly, which is just doing the same point in the other direction. The greatest philosopher of physics in the first half of the 20th century was Albert Einstein, and in the second half was John Bell. And they didn't have philosophy degrees. Mm-hmm. Mm-hmm. But they had the intellectual equipment to do good philosophy.
Right.
And did it.
Right.
So that still seems to... maybe we're arguing over something that is uninteresting to people or doesn't need to be argued, but in so much as I sort of reframed my point away from talking about philosophers and toward talking about philosophical thinking, it seems like you are agreeing with me that this philosophical thinking is very important and there are still deep philosophical problems.
Oh, yeah.
Okay.
Maybe here's a way to put it in perspective. There was you look at the way philosophers attended to physics in the early part of the 20th century, people like Reichenbach say, well, I don't even know if Reichenbach is a good example. There's a certain way of philosophers attending to physics, okay, where it does seem like there's a clean distinction, there's a clean division of labor, okay, that you're used to getting a theory presented to you, which is for certain kinds of standard scientific purposes finished, a finished product, a finished object, and what you're supposed to do is clean up the vocabulary a little bit, lend an ear to these possible confusions or ambiguities, and reconstruct the theory in a way that's supposed to give you in clearer language what you're presuming the physicists had in mind in the first place, in conceptually clearer language, in logically clearer language, so on and so forth. The advent of discussions of the measurement problem, and now I'm just citing a sociological and historical fact, changed that very dramatically, okay? The attitude in physics, okay, was that there was no such problem, or that the problem was merely verbal, or that the problem was merely philosophical, or something like that, okay? And it was the opinion, like I said, ironically, of people employed in philosophy departments that the physicists didn't understand that this was a scientific problem, okay? And so it became our task as we understood it, not at all to engage in the kind of activity I was just describing, but to forcefully tell and clearly say why the physicists were misunderstanding the physical project itself, okay? And that the physicists were doing physics horrifically badly, okay? And I must say, I think both Tim and I had the experience, because our ages are not too dissimilar and so on and so forth, in going through this, that this led to a much more exciting and fruitful kind of relationship between people working in philosophy departments and people working in physics departments than you commonly ran into before that.
Well, I think that this is a good time to stop, and it's been a lot of fun, and I enjoyed getting to argue a little bit as well there at the end. But thank you two again so much for doing this with me. I think you're the two most appeared guests on the show, so it's always great, and I'm always so appreciative of it.
I'm like Joan Rivers on the Johnny Carson show.
It's very nice, look, that you have us on and a whole array of other people in this area. I mean, you certainly have covered a lot of different approaches and aspects to this. I gather that people are interested, which is nice, and I really appreciate how much of your time you have devoted to these issues, and so thanks to you.
Me too, Robinson.